wait. Okay, so today what we're talking about is sensor characteristics. So this is obviously a huge part of your robot is sensing its world, sensing around the world around it, and then acting upon it. So the second part of this, acting upon it, is what we'll talk about more in the navigational lectures. This lecture is going to be concerned mostly with what sensors are available, how you might use them, and stuff like that. So I'll be talking about some of the main sensors you either have in the robot or possibly could see in the future. So some of this stuff isn't applicable to your kit, but still interesting if you want to take this project a little further. So that will include some of the different types of distance sensors. But most of this is directly applicable to what you have in your kit, and I've tried to keep it that way to make it as practical as possible. So sensing your world. So this is the star-nosed mole. This is one example of various types of sensors. So this is a head-on view of it. And if you want, you can watch a little video about it. It's quite interesting. But there's all sorts of biological sensors, and when we're dealing with the robot, we're going to be looking at equivalents of that. So it's worth sort of having some common terminology, because whether it's biological or electrical, a lot of the same principles apply and a lot of the same thought process. So what is a sensor? A sensor is a device that provides information about the physical world. So there's a pretty vague and sort of broad definition of what information can be seen as. So the world around you has information in it. What's the room temperature? That's a really simple thing to sense, but also you could claim it's a sensor of how is someone feeling, sort of vaguely like that. So this information has this really generic term. Anything which detects this information around you is a sensor. A more sort of direct, sort of well-defined term is what we call transducer. So transducers are converting energy from one form to another, and that's all they do. It's possible for a transducer to be a sensor, but not always. And a sensor can involve a transducer along with some other processing to get the final information out of it. So as an example, a microphone converts energy from one form, the pressure, variations of pressure, aka the sound waves, into electrical energy. The speaker does the opposite. It converts electrical energy into variations of pressure, aka the sound. Many of them are bidirectional, so LEDs, for example, they convert electricity to light. They will actually do a fairly poor job, but you can use them as sensing devices as well. So they will generate small amounts of electricity based on light coming into them. So you can use them in reverse. A lot of the time they're designed to work one way more efficiently, but they will work bidirectionally. Some work just as well in one form or another, so a motor and a generator. They're both transducers. They're either converting rotational energy into electrical for the generator or electrical energy into rotational. And for the most part, you can consider them the same physical item. There's no optimization. So the types of sensors that we'll look at, there's, as I mentioned, this idea of direct transduction. So these are the sensors where all they are is a transducer. So they just have this device that's converting energy from one form to another. There's no additional processing. You can use the transducer as part of a sensor to give us derived quantities. So stuff like, is there a human present in the room? Involves some sort of sensor that's doing or some sort of transducer that's, detecting heat or something like that. But then there's additional processing to detect the human. Or in the case of distance, we have various transducers being used to, as we'll see, emit sound and then wait for an echo and time the echo. But it's not a transducer that's directly giving us a distance output. We have some additional processing on it. So these are derived quantities. They use a transducer with additional processing to give us the item we want to sense. All right, so that's very basic, the sort of terminology we have on sensors. Let's look at what sensors we have for a robot. So the first thing is a distance sensor. The objective here is to figure out how far away some object is from the robot, and you'll see that in the course. Actually, that's what I want to show you. So let me just pull up the course. Where is it? Course loads. So you'll have distance sensors will be useful because, for example, when you start, let me just put this in PowerPoint so that I'm drawing it. Oh man. Okay, so you'll use distance sensors because where you start, there'll be various objects, and you can A, detect them to drive around them, but B, it can tell you some information about where you are specifically. I don't know why it's not. Some sort of issue with my file. Okay, there we go. So here's a course. So what we have is that when your robot starts off, it's starting out in this gate up here. And we're going to be using sensors to orient yourself within the course and find your way through it. So these purple blocks are physical walls right here. And when you set it down, you'll be able to set the direction so you might know which way it's facing. But you might say, for example, well, what I want to do is I want to drive, maybe you want to drive this way to collect these coins until you get to this object, or maybe right in front of the object, go over this way, something like that. So these distance sensors are useful because you could measure the distance between this wall here and where your robot is. And if you know that distance, you can figure out, okay, here's where I am relative to that object. I know where I am within the course, and therefore I can turn and do some other stuff. And the same thing, you could drive until you could look for this object here, and you could figure out where you are, that you're right in front of it, because there's suddenly an object right there. So distance sensors will can form part of your navigation solution, as well as obviously stopping you from just driving into stuff, which isn't perfect for your robot. All right. So back to this. So there's several methods of achieving this. Reflective, and the reflection can use sound, it can use light, or it can use electromagnetic, and there's names for each of these types. We could also use stuff like visual sensors. So your eyes for measuring distance there's basically the idea of using two cameras. If you offset them slightly, you'll see the change in perspective. Based on that, you can generate maps of the distance. So this is stuff like the Xbox Kinect camera, I believe, uses this, where it has two cameras to detect distance, as well as it's having some other systems. So that's more advanced stuff we won't directly be talking about. We're only going to be dealing with the reflective sensors here. So the most relevant to you, and possibly the most obvious, is this idea of echolocation. So echolocation, something that animals use, even bats use it in air, in water, dolphins with sonar and stuff like that. And basically all we do is you have something that emits a burst of sound, and you can see the sound wave going out. If there's a target in the vicinity, it reflects off the target, and you get an echo back. If you're doing more advanced processing, you could actually figure out stuff like what's the size of the target. Not only is there a target there, but based on the intensity of the echo, as well as the time delay characteristics of the echo, you can tell you a little bit about what the target might be. So rather than using like some sort of cyborg bat on your robot, we have this in your kit. And what this is a little ultrasonic transducer device. And it has two transducers, so it has one of these, I don't know which one, is a transmitter, and one of them is a receiver. And it'll emit a burst of sound at around 40 kilohertz, so it's above the point you can hear it. You will hear a little click as it turns on and off, but you won't hear the actual burst of sound itself. Is there a question, sorry? Or? No, okay. You won't hear the actual burst of the pulses. So for this device, it's a really simple idea. There's none of that, detecting what the object is. It's just, is there an object there or not? So if you have something like here, the idea is that, here's the object. You send out a pulse. It hits the object and then bounces back and is heard by the receiver. If you know the speed that this is moving here, so v, and we know what the time delay is between sending the pulse and hearing the echo, we can figure out the distance to the object just by multiplying the speed by the time and dividing by 2, because if we get the total distance would obviously, or the distance for the total time would be there and back, so we divide by 2 with the objective of measuring just this d here. And in practice, the transmit and receiver are so close together, so you can see in this system, they're like a few centimeters apart at most. You don't care, technically there'd be some error if it's doing this wide, if these two are quite far apart. In reality, they may be the same device even for some types of sensors, or in our case, they're so close together, the error is irrelevant to us. To use this, you need to know what the speed of that sound wave is traveling at. So in air, this works out to 343 meters per second, but it's important to note it does vary with temperature, so if you want to be more accurate, you'll have to compensate for what the temperature is to figure out the speed of sound. So as an example, at, I believe this was 20 degrees Celsius, it's 343 meters per second. Which is, pretty reasonable temperature. So taking just an object that's some distance away, this is a 10 millisecond time delay between start and receive. You can say how far away was that object? Well, doing this equation here, what you end up with is 1.715 meters, the obstacle's away. Now let's say we go up to 40 degrees Celsius, so not a massive increase in temperature, slightly hotter than the 20 degrees C. The speed of sound here goes up to 355-ish or 347.7 meters per second. So that's at 40 degrees Celsius. So using that same, if that was the actual speed of sound, it would mean the obstacle was actually 1.774 meters away. The end result is that you have about a 6 centimeter error on a little under 2 meters distance away. So it's a reasonable amount of error depending on your object. For your robot that's just doing, is something there, where am I roughly, that may be, you don't really care about that. Of course, if you're trying to do more accurate stuff, that could be a huge issue. So if you're making survey equipment or something like that, you would care about what the speed of sound was. But that's just one of the considerations you would have to run into to use these devices. So how they work, just sort of for your information, this is the circuit of this device here. So again, we have the transmit and receive, and on the back side of it, if you look in your kit, there's a bunch of chips and stuff like that. So what's inside them, I could show you quickly. Is this circuit here, and I'll just describe it for you. So at the bottom, there's a small microcontroller. So this is the microcontroller you have in your kit. Someone's made a program for this device. This is what's known as a one-time programmable, or OTP. It means you only have one, you can program it once, and then you have to throw it away if you want to change the program. So you don't get your program wrong, because it's not updatable. But the idea here is that someone's made the program, debugged it, got it to work, and then they load these, in the thousands or hundreds of thousands onto the chips to populate these boards and sell them, sell these things to you as cheaply as possible because the microcontroller is so low cost. So what that microcontroller is doing is you'll see a few lines here. So there's 4 pins on the device. There's an operating voltage, the 5-volt operating voltage. There's a transmit signal pin, which you have to set as like a 10 microsecond pulse to transmit. There's an echo receive pin, and then ground. So just for your circuit ground. So when you set the transmit pin, the microcontroller will send a burst through these lines to this, what's effectively the speaker, so the transmitter, and it sends this 40 kilohertz burst. It just sends 8 40 kilohertz pulses. And this circuit here is just being used, it's actually supposed to be used for something else, the chip. They've reused it to drive the speaker with very high voltages, like 20 volts, So it boosts up the 5 volts to give you a very loud sound. On the other side here, at the receiver, you'll see a number of circuits going through here. So there's some input for the microphone. There's an op amp which is used to amplify the signal. There's a filter, so this is to ensure, because there might be a lot of noise around you, there's people talking, whatever. So all it wants to listen for is this 40 kilohertz signal here, and this should be around 40 kilohertz. Some of the earlier versions of this, I think, had that set up wrong, but it still kind of worked. And then afterwards, I believe there's effectively just another amplifier here. So you can see, if you look at this in a block form, it's sort of fairly reasonable. It generates a 40 kilohertz signal, and then it has some circuitry that looks for that 40 kilohertz signal. And the microcontroller here is just controlling, everything, sending those pulses, and then waiting for the response. How you talk to it is just through this really simple system that you have to measure the width of a pin going high on. And if you want to experiment with this, you can set your, connect this to an oscilloscope, so you can connect this to 5 volts in the lab, connect the echo pin to a scope, a little scope here, and then the transmit pin, you've just got to generate a short pulse to make it send an echo, and you can sort of see how what the response looks like. So when you set the trigger pin high for 10 microseconds, it'll transmit those pulses. You don't see that, that's just going over the transducer. And then the echo pin goes high for however long it takes a pulse to be transmitted, hit an object, and bounce back to you. If no object was found, so it has a maximum range of like 20 meters in theory, I think, what you'll find is this pin just goes high for quite a long time. There's some timeout period basically, and you just have to say, okay, there's nothing there. So there is sort of one, well, there's a few caveats here. One thing is that you have your system here, the transmit and receive. You might want to do multiple tests of an object, because obviously if your robot is at a weird angle, it's possible, if you have an object like that, it is possible that you could transmit it and it doesn't see the echo if the echo goes off this way. They have a pretty wide field of view, so most reasonable objects it'll detect, but if you're at just the wrong angle, it just won't detect it. The other issue is that it could possibly be triggered by noise in the environment. So if it transmits and it's waiting for the echo, and in between that time, there's another loud sound that spans multiple frequencies in the gym. So if someone, drops a chair or something like that, that external sound might reach the receiver at just the wrong time. And again, this is why it's useful to, don't just take one distance measurement, take 5 and confirm that they're all reasonable, and either average them or just throw away, look for outliers in the data set. The other problem is that there's going to be 2 robots running the course, and both of these have the same sort of system on them. So they have the transmit and receive. So if one of you, transmits at some time here, if this guy's also transmitting at another time, that transmit pulse will be seen by the other robot, and it'll generate a false distance signal. Now this is all going to be random, because what has to happen is the 2 robots, so if robot 1 and 2, robot 2 has to transmit a echo at the same time that robot 1 is waiting for an echo response. So it's not extremely likely, but it could happen, especially if you're looking continuously. Again, another reason you might want to, every time you do a distance measurement, measure 5 in a row or something like that, and confirm, hey, this looks like a real object, and not just some sort of false echo. All right, so all we talked about so far is how those sensors work. The other question is, how do you interface them to the microcontroller board you have? As a sort of note, I have some links here. So this is a very popular device, this HCSR04. It's a low-cost ultrasonic rangefinder. It's used in a lot of applications and by a lot of people. The big upside of that is there's a whole bunch of examples and blog posts on using it. So I linked a few of them. Those are sort of just randomly found. But if you're having trouble with it, it's also worthwhile just seeing, hey, is there any sort of information or caveats that other people have posted. All right, so one of the first notes, this sort of side note number 1 is on AVR timers. To use these devices, you'll have to know how the AVR timers work. And I didn't have time in the programming lecture, so I wanted to cover it here, sort of as close as possible to where you might need to use it. So what the heck are timers? The most basic form you can see of this, all of the microcontroller timers are the same. There's some register, and what it's going to be doing is it's just using this register to count up. So it goes 0, 0, 0, 1, 2, 3, 4, 5, 6, and it's counting up at some fixed clock frequency. So timers are supposed to be used for all sorts of stuff, timing events, measuring pulse widths, generating signals of specific types. At the root of all of this is just a register that just counts at a very repeatable period. So we can use them, as I said, for measuring time. You can also use it for running code at very precise intervals. So if you have this register that counts up every 10 milliseconds, you could say, well, every 100 milliseconds run a piece of code, because every time this is incremented 10 times, if incremented 10 times, run some function. And this is what timers will let us do. They'll say, okay, we need to run this every 100 milliseconds always for testing that I'm not driving off a cliff or something like that. So you can set up a timer to always do that. You don't have to worry as much about, in your main loop saying, okay, did I run this function often enough or not? You just know it's always run 100 milliseconds. You'll also use them for generating a pulse width modulation, so PWM signal. In the motor control lab, you use one of the function generators to give you a PWM signal, but instead you can use the AVR's output to give you these PWM signals. And this will be, on your robot, how you control speed, very important. And finally, what will be of interest to us here is measuring the width of this external pulse. So going back to the what we need to do is measure how long that echo pin is high for, and we can use the AVR timers to do that. All right, so expanding our previous sort of timer block diagram just a tiny bit, we have the same idea of a timer register. So this timer register has the time, the count, and that count is, right now we're just considering being incremented on whatever this clock source is. So this clock source, you know, your AVR has a crystal on it running at some known frequency. Most of the time, or all the time, the microcontrollers also give you an ability to use other clock sources, which is either dividing down that frequency. The problem is that 14 megahertz might be too fast, so maybe you want this to run at 100 kilohertz. Or maybe at 100 hertz, or some slower value. So the microcontroller will give you an ability to generate some clocks, not any clock you want, but some amount of clocks. And the other thing we'll have is that when the timer reaches a certain value, a maximum value, which we call top, it resets back to 0. So, and the maximum value of that will depend on the size of the timer register. So that if this is 8 bits in this example, the maximum it could possibly count to is 255. There's no way it could count higher. We might have an ability to restrict it, so you know it only counts to 10 and then resets. It always counts to 10 and resets. But in this case, I'm saying the absolute maximum value is 255. So you can see the count sequence goes 0, 1, 2, 3, blah, blah, blah. 253, 254, 255, 0, 1, etc. So it's always just going through this count sequence. So here is what the actual AVR timer architecture looks like. This is pulled from the datasheet. So you can see it's, you know, this was really simple. We've gotten slightly more complicated. But if we look at each section of it, you'll see that it's very similar to what I previously showed you, and not, you know, not excessively complicated. There is a lot of features here, so don't get too confused when you look at the datasheet. There's a ton of features. You don't need them all at once. They just have them all there. You only need to use portions of it, and generally you just ignore everything you don't care about. So the most basic, we have this count register. So this is this TCNT, and what they say is N, and why they have N is because there's different timer numbers. So if I'm looking at timer 0, I would call this TCNT, timer count 0. So the timer count register for register 0. Okay, so the timer count. So we have the this timer register. So we have timer count 0 is our timer 0, and I'm just going to check the recording's running. It is. Okay. We also have, so they have added this control logic here. So this control logic is what allows us to count both up and down. Previously, I was talking only about, you know, counting up, counting up. So it actually has the ability to do both, counting up or down, which we use for some of the more advanced modes. The control logic also includes, so you can see in the bottom, they have this thing called top. And this is exactly what I showed before, which is there's some programmable maximum value. So the absolute maximum value is always, you know, if it's an 8-bit register, 255. There is 16-bit counters in this device too, but you can set it to some smaller maximum value. You can also set if there's a bottom, so if it's counting down, you can set, you know, only count down to some value and then reset back to the top. So there's all this programmability. Again, by default, everything initializes to sort of what you expect. So this would be 0, this would be 255. So don't worry about all the programmability if you don't need it. There's also, so we have this clock select here, and this is where I talk about you clock the timer however you want. So we have one option is a physical pin, can be one of the clock inputs. The other input is what they call from prescaler. And this prescaler, oops, come on, from prescaler. And what this does is this is, okay, there we go, from prescaler. And this is where we use the external clock and divide it down by some amount. And I'll show you that in the datasheet section afterwards. The other thing we have, so one thing I haven't talked about, all I talked about right now is just this timer exists. So some of the more advanced features include, there's what's known as an output compare register. And what this is doing is it's continuously comparing, so you can see in this figure we have TCNTN, and we have the TCNTN here. These two registers are the same. And you can see this is being compared to this output compare register. Whenever they're equal, so if the output compare register is equal to the timer count register, it does something now. In this case, what it's doing is it's going through we have what's this waveform generator block, and this can be used for part of our pulse width modulation. You can use this for really simple stuff, like every time the counter reaches some value, all I want you to do is generate an interrupt, which we'll talk about, which means every time the counter reaches some value, run this code, and just keep counting up. So it's going to always count up. You could go, if I go back to here, you could use this to say, every time the counter reaches 253, what I want you to do is run code. And I just program it to whatever value I want. So this lets me say, within the counter, every time it reaches this, run this chunk of code. That's one thing you can use the output compare for. This is also the basis for how the pulse width modulation works, which you can go through in one of the labs if you want a little more detail of that. The pulse width modulation stuff uses a whole separate block, which is this waveform generator block here. Very briefly, how that works is that we have our count. So if we have our timer counting up, if I go across, and let's say 16, 17, 253, 54, 255. And then it could either reset back down, and there's two modes. One, it just resets. In the other, it starts counting down. And for the pulse width modulation, if you remember pulse width modulation from the lab, is just where we have, what we want is some delay in here. So we have a repeating sequence, but it's only on for, say, 20% of the time, and then it's off 80% of the time. So this would be a 20% duty cycle. So how we can use a timer to give us this is what we could say actually, we'll take that external pin, and I'm going to program a value where it goes high, say 3, and I'm going to program another value where it goes low, say 17. So as the timer's counting up, all it's going to do, the external pin will be low, 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 low. It's going to go high at 3, because that's, I can change this. And then it's going to keep going high, and it's going to stay high at 17. It's now going to go low. And then it'll loop back around and continue. And what we end up with is this waveform, just keeps repeating. And this is what gives us our pulse width modulation. So normally what you do is you just go high at 0 and just set some value where you go low at. And whatever you set that value that you go low at is now going to give you a, directly related to the duty cycle of the output. So if I change this, so it just goes high here, and then says goes low at 17. And again, the scale is way terribly wrong, as you can see. So ignore the fact this looks like 50% duty cycle, because this is really 17 over 255, something around that. I might be off by 1. Of the time that it's gone high at. So that's how we can use timers for pulse width modulation. Right. The other thing, and this is what, this whole sidetrack was because we wanted this, is what's known as an input compare register, which it's not actually, if you're looking at the data sheet, you won't see it in the timer 0 device. You'll see it in the timer 1 and timer 2 devices both have this. All this is a register where, so we have this timer register. Oops. Why does this not? We have this timer register, and what's going to happen is that based on some external input, so you can see we have this input pin here, this ICP, it would be ICP1, so input capture pin for timer 1. You can also use some of the analog comparators, but when it occurs, and it being whatever event we've programmed, so we can say either a rising or a falling edge on that pin, when that occurs, it copies the value of that timer to some internal register. And what this means is that we don't have to set up code that does this. We can just say every time this pin goes high or low, record the exact moment that occurred at. And this is extremely accurate because it's all done in hardware. None of the software that's waiting, just like, oh, you know, there's a delay because I was doing something. As soon as it happens, it copies that register over to the input compare register. Okay, so that's sort of a very brief overview of the timer functionality and the timers in the AVR. Are there any questions on that before I sort of start using them briefly? Nothing too unclear? Okay. So going back, you know, slowly becoming unsidetracked, our problem that we had here was we want to measure this width of this echo pin. So there's three possible ways, now that you've seen a timer, that you could do it. The first is the simplest, and all I do is, in this sort of crappy AVR code here, I'm using timer 1. Timer 1's a 16-bit timer, so assume I set it up already. I'm going to write the value to 0, and the timer's not running initially. And I'm just going to wait. So I'm going to wait in software until that pin goes high. As soon as that pin goes high, I then start the timer, so I start counting. And then I wait again. I wait until the pin goes low. As soon as the pin goes low, I stop the timer. So it's no longer running. You always want to stop it because otherwise it'll continue to run. And you know, if there's some delay before you read the value, there might be extra counts in there. If you read the value right away, it doesn't really matter because you would get the immediate value out of it. But I now know the delay is whatever, because the timer, I started it at 0, and the delay is going to be, you know, whatever this timer counter value is, and that's the pulse width, related to the pulse width. So that's way number 1. This is probably, well, there's a few downsides to this way. One is that we're just killing time, so we're just waiting for that pulse to go high. If we wanted to do other stuff, you know, we didn't know it was going to go high right away, we might want to do other stuff at the same time. So another way to do this is to use something called interrupts, and I'll talk about those in a little more detail in a second here. Interrupts, basically, we do the same thing. So I set up a timer, and what an interrupt does is an interrupt just lets us, I have this other function here, so this can just be your main robot code is running all the time, stuff like that. And I have an interrupt set up that whenever the pin value changes, so if the pin goes low to high or high to low, it runs this little block of code here. And within this block of code, it just checks and it says, well, if the pin is high, that means the pin went low to high, so let's start the timer. And this part's just the same as before. So I, you know, reset the timer, set it to 0, start the timer. If the pin goes low, I stop the timer and I save the value. Within the main loop, all I'm doing is checking, hey, did I ever finish, you know, did I ever save a value to that register? If so, it then prints what the value is, and it's done. So the final way, and this is what's shown in one of the labs, the 3204 labs, is use the ISR, so the interrupt service. This is the interrupts again, except I'm using it with the input capture register, sorry, I meant to say. So in this case, I'm actually using the hardware to do the measurements. I no longer have any of the stuff where I'm starting the timer automatically. The hardware is dealing with all that for me. And you can see, so in this case, the only change I have is I'm switching from low to rising edge. And again, the lab goes through this in more details. I'm not going to sort of show you everything about this because it's slightly more complicated. But basically, if we want to measure this pulse width here, we'll generate an interrupt on the rising edge. So the timer will save the exact moment of that rising edge. We then have some time in here. We've got to configure it to say, okay, well, now tell me the exact moment of the falling edge. The exact moment of the falling edge. And you can see what we're doing is we're saving the starting count and the ending count. And then elsewhere in the main loop, we can subtract the two to give us what the time delay is. The only sort of caveat with this is that because the timer's running all the time, what you might run into is, my timer 0, 1, 2, 3, 254, 255, and then it loops around. So all of these transitions are at a very precise timeline. What's more than possible is the first edge occurs here. So it says, okay, starting time is 254. It then has looped around, so this is start, and here's the end. So it's looped around within the time. It's still a valid time. All you have to detect in the code is the fact that, hey, my starting time is after my ending time. So, if start is greater than end, it just affects how you do the subtraction. Because now what you need to do is you need to do start, oh crap. It cleared on me. So it affects how you do the subtraction, because now rather than, let's put this back here. Your time is not the time directly between them, but the time is from here to here and from here to here. So you just have to add up those two segments to give you the time delay. So sorry, it keeps clearing on me. But all of those details, so there's sort of, you'll have to experiment with that a bit and see, are in this lab, this ECED3901. So if you haven't used the AVR timers, or you want to generate pulse width modulation signals or use input capture, all of that is in this lab, and I believe there's a video to go with it too, so you can sort of watch that and see how it works, and then try it around. Experiment with it a bit. None of the labs are going to use this because there isn't enough time for this specifically. So I highly recommend, if you do want to get it set up, to see that reference. Any questions on that timer stuff? Timer stuff? No? Okay. There's now a second side note, which is the AVR interrupt. So this is another programming aspect that we've sort of briefly mentioned, and I already mentioned it in this lecture once. And this is what are interrupts. So the examples I gave you previously had what we would call two ways of doing something. This way is what's known as polling. Polling is I'm just waiting until something happens. In the second way is using interrupts. So when I use interrupts, I actually measure the, I let the microcontroller do something else, and then the correct code is executed for me. So what this means is that the microcontroller, I set up the microcontroller to say when this event occurs, run this code. And this code, does whatever I want. It's doing the measuring of the time, stuff like that. So you can, new data byte, I have some examples of interrupts there. New data bytes is received on the serial port, some data lines changed, or the amount of time has passed, whatever it is. All these are things that, you could just sit there and wait and say, okay, has this happened? No. Has this happened? No. Rather than that, you can just use the interrupts to say, okay, when this happens, do this, call me back. Very briefly, how you use interrupts, you have to include, so there's this include avr/interrupt.h. We then have this interrupt service routine macro, which has the vector name here. So the ISR with whatever the name is, so the vector name is the name of the interrupt. So the interrupt will be like, did I get a new data byte on the serial port? And that'll have a different name than did my timer overflow. So that's just the name, and whatever you have within it, the user code will run. The only other thing you need is this SEI, which is set interrupt enable, or set enable interrupt, something like that. This sets interrupts to run. There's another macro you can use called CLI, which will stop interrupts from running. So whenever the interrupts are running, these ISRs can all execute. So in our program, so we have this little while loop. If you're doing whatever you want in the while loop, if an interrupt happens, it's going to finish executing whatever the current instruction is. So if it's loading something from memory, adding something together, it's then going to store what the next instruction will be that it's going to execute. So the next instruction, maybe it was partway, it finished the load. The next thing it was going to do was add that value to a constant. It's going to say, okay, well, here's the next thing they'll do, store that. It then jumps to the interrupt service routine, or ISR. So this code here executes all of that code and then returns back to whatever the next thing to be executed on, and then just continues on, with its life. So those vector names I sort of mentioned briefly. You can see in the datasheet they have this interrupt vectors in the microcontroller. So we have, for example, the pin change interrupts whenever the pins change. We have some external interrupts. These are specific pins that you can use for doing interrupts. And we see at the bottom, you start to see a few of these timer ones. So there's a whole bunch of them if you look in the datasheet. And so the timer counter 2 compare match A. So this is one of those compare registers. When I said you can tell it, whenever this counter reaches 252, run this code. And there's a few different ones within each counter. So you can say, A, B, or C when it matches this value, do this. This other value, do this. So it gives you a lot of flexibility. The only sort of caveat is there's another link here to the AVR libc ISR vector names, so interrupt service routine vector names. And you should always use, it's critical you use these names here. So this int1 underscore vect, it has a column at the top telling you. And it'll list for what microcontroller they're valid for. There's a few cases where there's similar sounding ones that are only valid for one microcontroller or the other. As an example, there's this timer counter 0 overflow. Timer 0 counter overflow means the timer has reached the maximum value and has gone back to 0 or whatever the minimum you've programmed. So you can see, for example, it has this one name for almost all of the microcontrollers, and it has this other name for just a handful of them, none of the ones that we're using. But if you just scan through the list really quickly, you might get the wrong name. If you put the wrong name in, it may never get called, so it's not ideal. Or when you try to call your interrupt, bad things will happen because it has no way of handling it, even though you think you've set it up right. So that's sort of one important caveat to check for, is if you use interrupts, either check the name in this table, or if you're finding you have an example of someone else with the same processor or very similar processor, it should be fine. But if you're pulling an example from something like an AT Tiny, which is quite a different chip, then you might run into this. Lab number 4, the same lab as the timer stuff, also includes some examples using interrupts. So that lab, you can learn a little bit about both of these and experiment with them. The other sort of problem you can run into is what's known as the volatile keyword. So volatile tells the compiler, hey, things happen that you don't know about, and I'm telling you that, so you need to respect me. Basically, in this example here, I have this integer, it is done. And I set this to 0. I have an interrupt, and I don't care what it is, and I set it is done to 1 in that interrupt. Now what my main code does is it just, you would have to set up interrupts to actually have this run, but it enables interrupts, and then it just has this while loop, and it checks it is done set to 1. Whenever it is, it breaks out of the loop and prints that it is done. The compiler will look at this code, and the problem is it has no idea when this interrupt is called, so it just says, well, maybe it's never called. That's what it assumes, because it has no way, there's nowhere that you explicitly jump to it from within your code. It just sees, okay, you run this weird macro, SEI, and then there's a while loop. And that while loop will never exit in its mind because it is done was set to 0, and there's no way to set it to 1. So to fix this, we have to add this volatile keyword, and it tells the compiler, hey, always check the actual value of this variable because it could change in ways you don't know about. In ways you don't know about, this is, the interrupt. So any value that you set in an interrupt that you want to read outside it, you need to declare volatile to avoid this. If you're using variables within the interrupt, it doesn't matter because the compiler isn't doing that same optimization. It's only when it changes outside of the interrupt and inside the interrupt. So to use the interrupts, I have this quick checklist. So the peripheral itself, like the timer, for example, if you want an timer on the interrupt, it has a specific register. So for the timer, it's like time mask 0. And you say, enable the interrupt that does the overflow when the timer overflows. Jump to that. So you've got to do it there. You have to enable interrupts globally. So this is this SEI macro here. So that just has to be at some point in your code before the interrupt will run. You have to read the datasheet and figure out if you need to clear the interrupt flag. So once the interrupt runs, the problem is that what you don't want to happen is that it immediately runs again. So if you're interrupting when an external line is low, if that line is held low, your interrupt would just keep running, and your code can't do anything else because it's going to run forever. So you need to figure out how you clear the flag. Clear the flag. If you don't clear the flag, the interrupt will also just run again. So even though the event only occurred once, the compiler might think, hey, or the microcontroller thinks, hey, I should run this interrupt once more because this guy never dealt with it. So you need to clear that flag to say, yes, I have dealt with this interrupt. You don't need to call the code again. You need to check that any variables you modify inside the interrupt service routine that the main loop might need to read the value of are declared volatile. As I mentioned, anything inside it doesn't need to be. And you want to check it's not too long. The problem is interrupts, your code's doing something else. Your code could be changing the direction you're driving. And in the middle of that, an interrupt can fire. So unless you explicitly disable it, it'll just fire any time. If you have this really long interrupt that's calculating pi to 20 digits and all this stuff, your robot's still just going to be spinning in circles while your interrupt's running. So you want to make sure it's not a really excessively long interrupt. Normally you try to do as little as possible, just read a few values, set a few registers, and return to avoid affecting your main code. Right. So that's sort of any questions on the interrupt stuff before I get back onto the sensors lecture. And as I mentioned, there is the 3204 lab has some details on this too. All right, if not, some other distance sensors very quickly. So this one is not in the kit. It was in previous years, but instead they switched to the ultrasonic one, which seems more reliable. So other things you can do is you could use reflective angle for infrared. So this is a really simple method of doing distance sensing. So you send out a pulse, or in this case it's an LED, and there's a lens and stuff. So to make a small point, you could see it like a laser. And if the object's very close, you'll get this reflection off the object, and the spot would fall further along this position-sensitive detector. So you can see it's falling right at the edge here. Alternatively, if the object was far away, what you would get is it's only going to fall halfway on that position-sensitive IR detector. So you might have different locations within the system that the position-sensitive detector is sort of reaching. And based on where that reflection is lying on the this linear detector, you could figure out what's the distance of the object away. So that's sort of a simple reflective angle sensor. It's fairly limited in what ranges it has because you've got to tune it such that your reflection's always falling within this little small range. So the range of the ultrasonic ones is a lot better than these little IR reflective angle sensors. And because of all the optics required, these are quite expensive, which I don't think they could they couldn't give as many other sensors in the kit when they had these ones. So the ultrasonics are much more interesting. You can also do time of flight, and you can use lasers instead of using the ultrasonic system. So using lasers is more complicated because we have the same problem. We have a transmitter or receiver. With the ultrasonics, this V is equal to 300 and what did I say? 32, 43, right? Meters per second. So these delays are in milliseconds. That's something your microcontroller can deal with. All of a sudden, if we're talking about the speed of light, you can't use your little AVR microcontroller to measure this time delay anymore. It's just not possible. So the hardware becomes more complicated, and you use another method of doing this time measurement, but the basic problem is the same. The advantage of LiDAR, which is this laser-based imaging, is that it's much more, it's a much smaller spot. So when we consider the sound wave, you'll note that it will always sort of go out like this. So if there's an object somewhere, it's just reflecting back. And it's very hard to tell, for example, if we have our transmitter and receiver, is the object at position A, B, or C? Generally, it's just giving you an echo. You can't really tune it because the transmitted wave is becoming so wide, especially further away. You don't have you can't get very fine resolution picture. You just sort of know something's there. Because the laser beam is so accurate, you can do this even from satellites or from a plane. You can do this as like a city, topographical map of a city. Because even from a kilometer or more away, the laser spot size is so small. You always know when we have the transmitter again and the receiver, it's not going out like this. It's simply following a direct path. And that receive echo is only going to come if this object is right at position A. If it's just above it or just below it, there'll be no echo. So the advantage of LiDAR, or the main advantage, you get this much more accurate picture. Because of that, the LiDAR system is almost always scanned, so you'll never see them where it's just one little thing that's randomly pointed around. Normally it's scanned to give you a map like this. As an interesting note, there is recently that someone sort of come up with this very low-cost LiDAR module, so like $90. And it's using the same sort of laser system. They've done a lot of custom hardware. If you're interested in it, you can look. I just mentioned it because it's amazing that it's no longer in the thousands of dollars. It's in the $90 range for doing actual LiDAR. All right, so some other things you can do. Everything we're talking about before this was, detecting an object at a distance. You physically can detect it, like, dogs with whiskers or stuff like that. Detecting when an object becomes very close to them, and then instinctively will shut their eyes. They know something's, right there, so to protect their eyes. And you can do the same thing with your robot. So you can make robotic cyborg whiskers if you want. And to do this is just sort of a random example. These type of whiskers just use a little piece of wire. Unfortunately, you need something like piano wire, which I don't think is in your kit. But you could try it with some of the other wire and some support or some of the aluminum pieces. And you can see that if that whisker's pushed in, what's going to happen is, oops, I drew that wrong because this is where the whisker goes. So if you electrically charge one connection, it's just pushed against, there's a little pin, I don't know if you can see it too well, there's a little pin at that red point, and the whisker gets pushed against it and completes the electrical connection. What you do have in your kit is these micro switches, and you can use these for almost the same thing, except we tend to call them bump sensors instead. And you can see a lot of robots will have this. So this is the underside of a Roomba, for example. And basically, you just have this, half moon type thing you've made. And this half moon you can make again. You have the aluminum strip, which is perfect for this. And you have somewhere in here, you have these micro switches. And the idea is that draw this better. So you have your robot base here. You have the micro switches, and you'll have to support it properly. But if your robot runs into something, you know, if there's pressure here, it'll hopefully also hit that switch in. If there's pressure up here, it'll also hit the switch in. So you can kind of try to set it up such that no matter where it hits, it's going to depress some of these micro switches. So the bump sensing is it's always a good fail-safe in case you fail to see an object, and B, it is a good way, especially if you want to do wall following, you want to navigate just around an object, or you want to detect when you've hit something, like you have to run into the switches in the cores, so detect when you've actually physically rammed into them. All right. The final thing to mention in this lecture, I'll briefly cover one more after this about the navigational sensors, but there's a whole other lecture on navigation, is the optical sensors. And this will be the lab on Monday. We'll be dealing with the optical sensors. So you have a few types in your kit. You have this ambient light, reflective, transmissive, and what you don't have is this final one, what I'm calling multi-pixel, which is basically a camera. So a camera can be used as quite effective as a sensor, like for doing some of this stuff. So if you're doing, ambient light sensing, you can just use a camera and do processing on that. Instead, in your case, you have physical sensors that are detecting all this. So ambient light, you'll be using to detect a light source. You could also detect, is the room I'm in darker, light, not darker, stuff like that. A really simple application of that in a robot is these beam robots. So these are really, the idea is very straightforward robots. This one just has, there's 2 solar cells is the idea. And depending on which solar cell has more light, it actually drives the robot towards that light. So it's sort of like a little moth thing. So if we have a bulb over here, this solar cell is going to be getting more light. And you can barely see, there's sort of 2 motors here. And it just drives the appropriate motor to slowly walk the robot towards that light source. What you have in your kits is this ambient light sensor. So this little guy can do, and it can do up to about 1 kilohertz, so you can detect a modulated signal. Again, on Monday you'll see more on that. And this is a phototransistor-based light detector, and it gives you sort of a changing, you could think a bit like a changing resistance value with light. So what it really is a changing collector current. We have a little, no. So there's a little schematic in the data sheet, but basically the symbol we use for it is something like a transistor. But rather than there being a base lead, there's no base in this, we just have light comes in. So as light increases, it allows more current to flow, which changes the voltage. So if we have VCC, we have a resistor, and this is V out. So this little circuit here would let you use this light sensor. It replaces what you probably have used or are more used to is what is called, is this type here, CDS. And these light sensors you saw in everything like an outdoor, motion sensitive lights that turn off during the day and stuff like that, always had these crappy little light sensors. They're really cheap. They're not as popular anymore because the cadmium in them is banned under the European Reduction of Hazardous Substances Directive. Because of this, you more or less can't use them in Europe for a lot of applications, and people are now using alternatives. I don't know if that's why they're not in the kit. These are slower is the other downside, so they're good for detecting, hey, there is a bright light here. It's not as good if you want to detect, like with these guys, what's the frequency of some light source. So these are a lot nicer of a sensor, but I just want to mention, you might have seen these before, and that's why they're becoming less popular, is because they're banned under the European directives. The other type of light sensor in your kit is a reflective light sensor. So these reflective light sensors have 2 devices. Do I have a little thing? No. So one of these is a transmitter, and one of them is a receiver. So this is different from the distance sensor I showed you. You know, it was able to detect what the distance away was based on the reflected angle. There's none of that. This is just saying, is there a reflection of the light? And what we're going to use that for is on the robot course. Let me switch back to that. There's a bunch of spots that, so this sort of a, I don't know what you call this, dark red border everywhere is actually reflective tape, so it's just a silver tape. And using the reflective sensor, you can detect if your robot is about to drive over this silver tape. If you're driving over the silver tape, bad things happen because there's either the edge or there's this hot magma here, which is really just an indent that your robot will drive into and get stuck. So what you will want to do is use the reflective sensor, you know, mount it out a little bit to see, go back to this guy, to see that your robot is, to see that that tape is there, because you'll suddenly get a very strong reflective signal. And this will require tuning, so some of the output power of the diode, as well as, it has the same idea as the phototransistor, where when it detects light, more current flows through here, and that gives you a voltage output. So you just have to adjust what the standard current flowing through it is based on the light. So this is really R2 is the critical one to select, and it depends. One thing you have to be careful of is temperature variations. So you can get, you know, about easily half the output power with, you know, a 10 or 20 degree temperature change if you've sort of selected this wrong. And you could be testing the robot down here, you know, in 20 degree weather. It might be a hot day in the Sexton gym and it's 30 degrees or so in there. So temperature variations will be important to consider. And all this really means is that you'll have to go through the design. Again, the lab will show you how to go through this design to select a proper value, rather than if you just pick some values and it's like, yeah, it seems to mostly work. You might run into this where actually when it gets hot, it doesn't work as well. Or that might be something you want to test. You know, get a hairdryer and make sure when you have the hairdryer not too close to your robot, you're not melting it. But when you've brought the temperature up to, you know, 40 degrees, it still works very reliably. So that's a really simple thing you can test, which is nice. And in the data sheet, it tells you, so there's a distance away. So this is the current, and this is just a relative value. So it's not actually 1 milliamp, it's just 1.0 relative to whatever the maximum is or the normal current is. And you see there's a distance away. So as the reflective surface gets further away from that sensor, the current falls off. The unit here, mils, by the way, 1 mil, typically I think what they're using is 0.001 inches. It's sort of a confusing unit, but it's been used for a long time in mechanical and also circuit board layout. You see it all the time. So this, for example, over here is equal to ½ inch, which would be like 1 and some centimeters, right? Yeah, 1.25 centimeters, something in that area. So you can see that it's really for detecting a very close object. Once it gets further away, the signal will drop off. And that's sort of the reflective tape that'll be everywhere. So it's very reflective. So it should have no problem seeing that. And contrasting it with the regular, you know, plywood that'll be painted some darker color. The other type of optical sensor you have is a transmissive, and you see this in wheel encoders. So this is an old, if you ever use the ball type mice, not the nice optical ones, how they work is there's a physical trackball here, and you can see it's rotating. There's these discs here that it's rotating, and what those discs do is those discs have little slots in them, and there's a infrared transmitter and receiver. So one of these, I don't know which is transmit. This one's probably the receiver because it's black, so it's shielding from everything but IR light. And all it's doing is it's looking for, you know, hey, if I see a big pulse, then nothing, big pulse, then nothing, I know that this wheel has moved past a certain number of times. So all it's doing is counting the ticks in that wheel. On your robot, you have these These ones, so this is part of a circuit board Mark gives you. And this circuit board, you basically have to solder that in, select some values, and you need a encoder wheel as well. And you can sort of see, let's see now, there's a little bit of a dip in there. I don't know, you can kind of see it in the photo. Basically, there's this slot here. This is where the infrared transmitter and receiver is. So it's designed to, count slots going past it. So what this means is you need this encoder wheel. Something, this is not exactly like the one you would need. Mark has some of them if you want to take a look. The only thing is that you will need to design it. If it's not in the kit, they give you some of the 3D printing material. All of the computers have Solid Edge or SolidWorks. Do you know which ones they're using now? SolidWorks is the... Okay. Yeah, they switched a while back and I forgot. Anyway, so they're using this, and if you have questions on the 3D printing, you can see Mark. He's going to send out some deadlines, so I think one will be at some point in the next week or two. He just wants to print a batch at once, and then he'll print another batch towards the end of June. But there'll sort of be some more details on that once he gets a deadline. And again, these are the same phototransistor outputs, so it's the exact same problem that we were having here. Selecting these resistor values will be critical to getting operation, especially over variations in temperature. And then you can use those signals to figure out where you are. So we'll talk, the figuring out where you are part is what we'll talk about in the navigation lecture. For now, all you need to know is that this encoder disk and that phototransistor form a sensor. And the encoder disk itself, so if you start to assemble the robot, you'll sort of see a part that it can fit on. So here's the wheel. You have the motor here, and there's another shaft at the output. So basically the disk goes right here. The disk just turns with your wheel, so you can tell how far your wheel is turned. All right. So the final thing to talk about is metal detectors. So it's more than just for finding lost stuff on the beach on vacations. The basic principle we'll talk about, or we'll use, is this idea that you have a coil, and that coil is part of which is an inductor. Oops, it's not a very good inductor symbol, sorry. That coil is an inductor, and we're going to use what's called a tank circuit with that. So a tank circuit just has some resonance frequency that we excite it with. And whatever the resonance frequency is, if we excite it with that, you should be able to measure a larger voltage. We'll then detune the circuit by bringing metal near the inductor, which will change the inductance. That's the main method we use. You could in fact detect variations in Earth's magnetic field. You have another sensor, the magnetometer, but it's not quite it wouldn't be as effective as just using this really simple detuning method. And the detuning method we'll talk about in one of the labs anyway. How the detuning method works is basically when we have a coil, if you bring a coil near a conductive metal, a bunch of eddy currents are generated within that metal. And these eddy currents generate their own magnetic field that in fact opposes the incoming magnetic field. There's sort of an interesting effect. I'll just show you this before wrapping it up. The field, of course, will oppose opposes what the inputs, or opposes what the field is that excited it. So, come on. What happens is that if you really quickly generate a field, you can see this disk just shoots off. And what he's done is he's dumped a huge amount of power into that device. There you go. So these are sort of fun. You can build them. It uses massive, highly dangerous capacitance. Don't worry about that. So you can see it just jumps off. And that's all of the eddy current stuff. So we use that same principle for a much less fun purpose, which is just to detect the metal, unfortunately. I wish you were using it for that. So again, in a few weeks' time, 2 weeks I think, there's a metal detector lab, and we'll talk about both a simple metal detector, which uses this idea of a tank circuit. The tank circuit gets driven, and you detect what the voltage on it is. as well as a, and this is to give you an idea, so this is a previous robot, and this was using the larger bases, not the smaller ones you have. But you can see there's just a coil of wire here. So this is one of, they had a two-sided metal detector. And what this is for is to detect the metal strips. So, oh crap. There's a number of metal strips, and the metal detector is able to sense these right there, so those metal strips. All right. And there's another version which amplifies the signal, so it can do a slightly better job of detecting this. Yeah, but as I say, more details will follow in lab number 5. So I think the rest of this stuff will be covered in the, most of this will be covered in the navigation. Very briefly, there's other detectors, so we can detect actual acceleration, which is basically, as your robot moves. This used to be done with a mass that would be connected to springs. There's now these very small sensors that do effectively the same thing, but you can see what we have is we have a mass, and it has a spring that's just keeping it at a constant moment. As you accelerate this, the mass is going to move within this, this sensor unit, and you can detect that, detect the change in position of the mass to figure out acceleration. And things like your cell phones will have these 3-axis accelerometers for all sorts of uses. Position, all this stuff is in the navigation lecture. I just wanted to give you an idea. The other sensor you have a gyro, which can detect rotational acceleration. So you have a wheel that's spinning along some axis of rotation, and it's solely detecting how fast is that wheel moving in whatever direction it's moving. So this is done with a gyro, and again, we have 3 axes, so it can detect movement in any direction. And you can combine all these into something called an inertial measurement unit. So they use these, in aircraft and missiles and stuff like that, because they're able to detect extremely fast changes, as it rotates, goes up or down, stuff like that. And the same thing for when we're detecting the Earth's magnetic field. So this is where the magnetometer comes in, which you also have in your kit, as there's just one chip that does all 3 of these. So this is detecting, like a compass, the Earth's magnetic field. We have a 3 axes because there's issues that the Earth's magnetic field is not perfectly parallel to the surface, but instead you'll see will actually come in at an angle. And as you tilt the sensor, this can cause us a lot of grief, which you might not realize because a compass can move slightly. The needle in the compass is able to move slightly, but that's the nav. And one of the labs is going to take you through how you generate an entire compass output based on accelerometers and magnetometers. So that's sort of it. So there's many sensor options in your robot. I hope I've given you some detail on the main ones you're going to use. You'll have to plan to experiment a little, either in the lab just using the generators, or ideally using the AVRs. If you haven't used the timers and interrupts, you really should do the 3204 lab. At least, you don't have to do the lab right up and everything. I mean, just look at it and say, okay, well, here's how you generate a pulse width modulation signal. It takes you through everything there, and you can use that then to drive your robot H-bridges. The metal detectors will be useful to sense magnetic strips, and a lab's going to take you through that. But you can also look at some of the, Dr. Gregson's manual goes through that a little bit. Same thing with the accelerometers and gyros and magnetometers. We can form to make a complete nav solution for heading. More details will be in the next lecture and in one of the labs. So, with that, any questions? No? Okay.